Well, thank you everyone for showing up today. We just had a great presentation on 96 boards and some of the offerings that are available, and I'd like to have an opportunity to talk a little bit about what we have in terms of the Ultra 96 board. Earlier this morning there were a series of sessions in this room on artificial intelligence, and I'll also address that a little bit. And then we had Tomas give a keynote this morning, and you'll actually see that he and I kind of think alike because our slide decks are somewhat similar, but I have a little bit longer time than he did, so I'll be diving into a couple of topics a little bit further than Tomas had an opportunity to cover. So we'll like to tell you a little bit about what field programmable gate arrays are, their value proposition, why you should bother using them. I'm curious, are there any hardware engineers in this room? There's no point in my asking about software engineers. There's a couple of Xilinx guys, another guy raised his hand. Okay, so traditionally FPGAs have been a hardware thing, and now we're trying to make them, and we are actually making them a software thing. And so I'd like to kind of tell you why they can be useful for you. We'll go into the concept of heterogeneous, all programmable devices. So we take the whole concept heterogeneous a little bit further than what you may be used to. Then we'll go into how do you go about creating code for it? Do you have to fear anything? Then I'll talk a little bit more about the Ultra 96 development platform. We'll go into our software acceleration design example, a little more detail than Tomas had an opportunity to cover this morning, and then wrap up. And incidentally, tomorrow at 11 a.m., I actually have another presentation, goes into even more detail about the implementation of neural networks on our devices. So inevitably, always have to start out with a marketing slide or two. I think as designers, especially if you're an embedded system designer, you're constantly challenged. You're challenged with how do I get this particular design implementation running in this system? How can I make sure it's fast enough, meet my power goals, and of course fit into a smaller box and be more cost effective? We are constantly being pushed to be creative, and at the same time, we've heard some sessions about security and reliability. How can I make sure that I protect what's on my device? How can I protect my intellectual property? And how can I make sure it's not hacked? And with the work that Xilinx has been doing for many years, we've kind of tackled all these areas. You can see that we've gone into many different markets, all the way from powering the internet infrastructure, wireless audio-video, cloud and data centers, industrial, automotive markets. We've pretty much done it all with our devices through our customers and partners. And we are now looking at even moving it broader. Most of you probably have not heard of Xilinx before this event. And that's because we've generally been sitting out there on the edge of and into the infrastructure, and we believe that we're going to be moving more and more towards the edge into this Internet of Things. And that's part of the reason we have the Ultra 96 board that we've introduced at this event. So what is a field programmable gate array? Well, I went to the authority, Wikipedia, and it says a field programmable gate array is an integrated circuit designed to be configured by the customer or designer after manufacturing, hence field programmable. So the best way to put it is, if you were to look at years ago, your hardware engineer went into a catalog, he selected a whole bunch of chips, he took those chips, wired them up on a schematic, laid it out on a board, and hopefully it worked the first time. And if you went to him and said, hey, can you go change that hardware design? He'd look at you and go, no problem, 3 months, I'll have it done for you. So something that was challenging, difficult, time-consuming. What the field programmable gate array does for hardware is what you and all of us have been used to for many years in terms of software. In other words, we create some code, we download it, we run it, we see if it works, and we go and debug it, and then make some code fixes and do it again. And with an field programmable gate array, you can do exactly that type of thing. Now, as you heard earlier, if you're at the keynote, what is inside of it? Well, we talk a lot about configurable logic blocks. And a configurable logic block, in its simplest form, can take on some very simple logic configurations. It can be an AND gate, an OR gate, or an inverter. As a digital designer, you learn at the very beginning those are your basic functions. However, because they're configurable, and our devices happen to have 6 inputs, they can take any logic combination of those 6 inputs and generate an output. Now, if you were a digital designer, you'd learn over the years that, hey, if you take enough of those, configure those, you can generate a flip-flop. Once you have a flip-flop, you have a memory storage element, and you can keep expanding from there. Cool. Okay, so we got these logic gates. The other piece of magic is that we lay down large arrays of wires that are horizontal and vertical, and which are basically traffic lanes to move the digital signals around. And so we have what's known as configurable interconnect. In other words, we can take the output of any logic gate and connect it to the input or multiple inputs of any other logic gate. And by logical extension, then we can create any arbitrary logic design. Now, obviously, you have to get information on and off your chip, and so we have input pins and we have output pins. And as you heard Tomas indicate, over the years, we discovered, hey, well, yes, we can create lots of flip-flops, but that's very costly in logic, so let's add some block RAM. Then we discovered a lot of customers were doing digital signal processing functions, so we added DSP blocks. And then somebody looked at one of our devices and said, you know, you got enough logic there, I can implement a state machine. Cool. And then somebody else said, you got enough logic there, in that latest generation, I can implement a small microcontroller. And so over the years, Xilinx actually invented a microcontroller. We call it the MicroBlaze. It's a soft processor that is just configured. Now you think, hey, that's probably pretty primitive, but if you start looking at today's latest generation of MicroBlaze, it has something, it has things like a memory management unit. It can boot and run Linux. All right, just kind of gives you the feel of what can be done with all this logic. Now, of course, if you think about it, inherently using all that logic to build things like a MicroBlaze processor consumes a lot of logic. So over the years we said, you know what, let's just start hardening other elements. And you heard at the original keynote that originally we started with a PowerPC, then we saw the light. And we implemented the ARM architecture, started out with an ARM Cortex-A9, now we're up to an ARM Cortex-A53 as our application processor. So we've been building this ongoing infrastructure in our devices to the point of where a lot of us start thinking more of it being a processor with a little bit of programmable logic rather than a programmable logic with a little bit of a processor in there. And so I kind of jumped ahead. Early hardware engineers, basically, we had a little bit of logic there, so all we could do was implement patches for designs, do simple state machines. We actually, over time, our devices got so many gates in them and so many logic cells, we actually had companies come in and say, you know what, I want to go build an ASIC, but I got to get it right the first time. So how about I go and use your field programmable gate array to implement my ASIC design. Obviously, it's going to run slow, but at least logically, I know it's going to be correct. And oh, by the way, Xilinx, we tend to eat our own dog food. So we actually build these giant boards with some of our latest chips. And last generation, we actually put 6 of our largest devices on the board. And we implemented in one of our devices the ARM Cortex-A53s, the whole 4 of them. In another one of our devices, we had the R5s and platform management unit, another one, the interconnect, and peripherals, and then another one, for some strange reason, we just had the DDR memory controller. But the point is that we implemented a complete chip within our devices prior to going to silicon. And we actually took out and fielded 100 of these boards into a board farm where we actually ran code booted Linux and things like that, so that we could actually test all of the silicon prior to actually going out and fabbing it. Why? Because fabbing silicon is a multi-million-dollar proposition these days. So again, I got ahead of myself. We have customers and partners that do a lot of bridging. You heard a presentation earlier where they were talking about their own custom chips, and they had an FPGA in the middle, basically moving the data back and forth and bridging it between all their devices. Digital signal processing functions, and again, complete embedded processing systems. One of my favorite topics over the years has been acceleration of software. This has been something of great need as we are moving forward. You heard from Tomas earlier about the fact that basically processing performance, clock speed is leveled out. So people go to multi-core, and multi-core is really great, but even there you start hitting some challenges. Typically it's memory bandwidth or just being able to move the data back and forth. And if you can create a custom compute engine inside that programmable logic, then you're able to overcome Moore's law. So, takes us to the next topic, the whole concept of heterogeneous and diversity. In other words, getting the right processing function or right processing element doing the right job. And so if you look at our devices these days, we have application processors for our general purpose computing, running Linux, doing user interface, doing complex logic or decision making, handling all of the I/O functions, Ethernet, USB, typical sorts of I/Os that you're doing with a general purpose computing. We have a graphics processor, ARM Mali 400, real-time processors. Any of you actually do any real-time processing? Okay, not in this group. So when I show up at a trade show such as Embedded World, Industrial and Automotive, and the guys that are out there, every single one of them is doing real-time. What's so important about real-time? Well, the important thing is that if you get an interrupt, you need to be able to respond to that interrupt with extremely low latency and do it in a deterministic manner. In other words, be able to say absolutely positively, I'm going to respond to that interrupt in under a millisecond or two. I can't wait around for an operating system in which it may be doing a page switch, waiting for it to kind of catch up with that page switch where then it can finally go and service an interrupt. And, oh, by the way, our R5s, as you heard earlier, they can be run in lockstep. Anyone know why the value of lockstepping two processors? Yes? Exactly. So, you got two processors. They're running together. You compare the output of the two processors. If they disagree, because one of them took a hop, skip, and a jump, and that can happen, then you can say, aha, I've got a system level error, and you can do what is known as fail-safe. In other words, you can stop operation immediately rather than go on and do something incorrectly, like hit the brakes on a car inadvertently when it's not intended. We have something called a platform management unit. There we put some of our most critical code. We have our power management code that runs there. We have a small scheduler that runs there. We have some other code that can run there. That's a whole nother presentation I'd love to talk about sometime. But what's also interesting is this is a triple redundant processor. Triple redundant, and that means you can put your most critical code on that processor. And it means, what's the value of triple redundancy? Why is it better than double redundancy? Make a wild guess.
Twice the amount of fail-safe.
I'm sorry?
2 times the amount of fail-safe. You can fail twice before.
Well, okay, you're almost right. You can fail. Yeah, you fail majority. Yes. So basically, with triple redundancy, you get all three that vote. If one of them has an error, he gets outvoted, and you throw his decision out, and you can continue operation for a while with just the 2 cores. Eventually, you do have to bring that 3rd core back online, get all 3 in sync. But again, for functional safety applications, extremely important. And when we're talking automotive, industrial control, avionics, any place where you can have something that's basically can't fail because human life is at risk, it's important to have this type of thing. We also have a configuration security unit. We have been working with security applications for many, many years. And we have a whole team dedicated to security. We want to make sure that any code, or what we call a bit stream, in other words, hardware configuration, is the correct code and hardware configuration that's going into the device, so we can authenticate, we can decrypt that code, we can to make sure that, again, somebody doesn't easily steal your code, so you can keep it encrypted. And depending on your application, we actually have some customers that retain critical code segments entirely within our device. So we have something called on-chip memory, so that the processor can run critical code on chip, never having the possibility that it could be snooped or attacked externally because you have this access to external DDR memory. Incidentally, that processor is also triple redundant. And then, of course, we have this programmable logic, typically used for additional peripherals, high-speed data processing, and software acceleration, which I'll talk a little bit more about. Now, quickly about custom peripherals. How many of you gone and out and bought a ASIC chip with an embedded processor and a whole collection of peripherals, only to discover you're missing a couple key peripherals? Okay, you all are software guys, so you probably was the hardware guy that was kind of stuck with that. You probably have seen it go on. Okay, and the hardware guy then has to go out and buy a special chip and attach it to your processor for that additional peripheral. With a field programmable gate array or programmable logic, you have this opportunity to simply say, you know what, I got 2 onboard Ethernet chips, but I need 4. And at Xilinx we say no problem, because we have soft Ethernet chips that you can just instantiate into the programmable logic. It's literally drag and drop with our tools, have it hooked up to the processor. Drivers are automatically added to your system for those peripherals, and voila, you now have 4 Ethernet MACs that you can use in your system. So, kind of summarizing advantages. So first, we have a performance advantage. We have the ability to accelerate software. We have performance advantage because of the ability to have tight integration between the processing system and the programmable logic. We have thousands of wires that run from the processing system to the programmable logic. A lot of it's on the AXI buses, a lot of it's for other control type functions. And so this means you don't have to go off chip. As you probably know, as soon as you go off chip, you inherently have delays, which can be very costly in terms of overall system performance. We have a power advantage. Again, by tight integration, you don't have to burn power on things like PCI Express interfaces unnecessarily. As you may know, PCI Express, high-speed serial transceivers, very power-hungry devices. And then, as you will see, with the dramatic types of acceleration we get, because we have implemented custom hardware on the device, we don't have all of the overhead of a general purpose processor. The net effect is we generally have significant power savings compared to a general purpose processor. And of course, as you've heard me talk about, infinite amount of flexibility. Time to market, you already heard me allude to earlier about the hardware engineer. Hey, now he can go and fix something immediately in the device. The ability to go and post-production in the field, do a field upgrade as easily on the hardware as you can do on the software. The ability to take a single platform and use it in different products simply by different configurations of software and the programmable logic for your hardware. So, again, we have, I think, a lot of software developers in here, and I think it's an interesting experience for those of us that have been involved in high-level operating systems and applications residing on those operating systems to address some of the real-world challenges of communication. And this is the typical classic thing, and here's an industrial example, robotics application, real-time control of a motor. And you have to be able to respond and control that motor down to millisecond levels. I think even some folks are doing hundreds of microseconds for motor control. And you can't do that with an operating system such as Linux, even with the real-time extensions. And so this is why it's really nice to be able to have your general purpose processor and your real-time processor as independent elements, and the RTOS running on that real-time processor. Again, deterministic and low latency access for your real-time processing. So, taking a look at the high level, what we have in the Zynq UltraScale Plus, we have a variety of different families. We start out with dual-core A53s, and with our EG devices, we go to quad-core A53s. You're pretty much all used to them by now because this is typically what we have in our cell phones today. Run symmetric multiprocessing, Linux. We have a family what we call the embedded vision devices. So we actually have integrated video codecs. We support up to 4K P60 or even 8K P15 variable formats, H.264 to 265. Anybody doing vision compression, decompression? Nope. Okay. Again, the A53s, you're familiar with them. We do operate up to 1.5 gigahertz on the A53s. The R5s, we operate up to 600 megahertz. Mali graphics units, the Mali 400. So it's, reasonable 2D, 3D graphics processor. I talked about the codecs. We support DDR3, DDR4, and low-power DDR memory systems. We do platform management. Now, this is a place where I always kind of get up and I apologize a little bit. Being from an FPGA company, we always think in terms of watts, tens of watts. We have some devices that consume over 100 watts. And so we live in a different world when it comes to power. Majority of our devices are designed to operate off of AC power. We do have many customers that do battery-powered applications, but I will call them, these are kind of man-portable types of things, medical instrumentation, large tablets, etc. So we have the full ability to do the things you're used to, like being able to take A53s offline, turn off their power islands. We have independent power domains for our A53s versus the R5, so we can do things like turn off the full power domain with the A53s, continue operation of the R5s. We can even go down to just having the platform management unit running. But if you were to ask me, hey, what's your lowest power consumption when everything's idle, I'll go and say, and I will proudly say, 35 milliwatts. I do acknowledge that it's a completely different world than, let's say, what the cell phone or the true tablet world is used to. But for many of our customers that are used to and needing really high performance data management and movement, these are wonderful things that we do offer. I talked a little bit about our configuration security unit, and of course FPGA acceleration. And then within our device, in the main processing system, we support PCI Express Gen 2, we have USB Gen 3, DisplayPort interface for the graphics processing unit. People ask, what about HDMI? Answer is programmable logic. Any HDMI standard you want, we support. So, again, advantages of this type of device. rapidly implement your designs, test both the hardware and software, accommodate your manager coming to you saying, guess what? Competition just introduced that new feature and you got to put it in your device and I want it done tomorrow. You can do it. The whole concept of field upgradability. We have customers that go and remotely update their devices, both the hardware and software via the internet. You can span multiple generations with a platform because you're able to upgrade both the software and the hardware. Dynamic partial reconfiguration, oh boy, a whole nother topic. Love to talk to you about an hour on this one. But this is something that's totally radical for the hardware world. You as a software engineer are going to go, so what? Okay, software world, we have been used to it for years and years, the ability to go and run an application and swap it out and run another application because we didn't have enough memory, and we have virtual memory. So we're used to the whole concept of having a limited amount of memory and swapping things in and out. Hardware, we can now do that. So that you can do things like, my favorite example is an infotainment system on a car. Well, you might be doing a video, so why not put in all the video pathway into our programmable logic to watch a video, and that may be different than what you might have for an audio pathway. Or it might be different than using that same head to display the video from your rear view camera when you're backing up your car. And you go, well, that's really cool, but so what? Why don't I just buy a bigger device? And at Xilinx, we're more than happy to sell you that bigger device, and it will cost you more. So what our customers like is, hey, they can use one of our smaller devices, save some money, save some power, by simply swapping in and out hardware designs. And of course, one of the challenges, if you are a embedded designer, software and hardware, is debugging the hardware and software at the same time. I'm sure you guys, some of you have at least had that wonderful occasion where the hardware engineer comes to you and says, here's my hardware design, it's all working. And you as a software engineer go write all the drivers and code and try to drive that hardware and go, it's not working. And the hardware engineer goes, it's correct, the usual thing. We even go through it in the software world with two software engineers. So we have the ability to simultaneously look at code and look at hardware and see exactly what's going on. If you do a write from code to the hardware, we can show you exactly what's going on inside the hardware in the programmable logic to demonstrate it's doing what it's supposed to be doing or not. All right, now that I've got you fully intimidated about what can be done with our devices, let's look at how one goes about using them. So, software development flow. The whole purpose of this design, or this slide, is to really say the software flow is no different than what you are used to today in terms of software development. You basically start out with a hardware platform. It says, here's all the hardware that's in your system. And then our tools who create the software platform brings in all the correct software drivers associated with the hardware that's in the system, generate libraries, you then create your code, you compile it, you link it, you debug it in exactly the same manner that you have been doing for years and years. It's a JTAG cable, which I'm sure many of you have been using if you're targeting an embedded processing system. You can, in terms of debug, you can do the usual single step through code, set breakpoints, third-party tools allow you to do trace capabilities. You can profile your software applications, figure out where your critical code segments are, hand optimize if need be. We have an Eclipse-based IDE development environment. It's Windows or Linux hosted. You can use the GUI, but if you start automating the process, there's also a command line interface, so it can be all scripted. And we provide everything you need. The board bring up firmware development, bare metal application development, Linux application development, performance optimization, and system deployment. A lot of words there. Incidentally, when you get the Ultra 96, you get access to all our tools to do this. Runtime software. This is kind of a who's list of all the OSs. I think a lot of us are very much Linux focused here, but we support both Linux as provided from Xilinx. We like to call it PETA Linux, but it's just a standard Linux build. We use the Yocto to go and implement the Linux system. But you can see we've got third-party partners, Android, bare metal, FreeRTOS. If you're into security or high reliability applications, Green Hills Integrity, Wind River VxWorks. You'll notice the entire list runs on the application processor. Our R5s generally run things like bare metal, FreeRTOS, and then any other RTOSs that are focused for real-time applications. And then the last column you'll see is labeled microblaze. Now, remember I mentioned microblaze as a soft processor. We have so much experience with the microblaze. So when we went and implemented a triple redundant processor, guess what processor we used? Obvious answer, microblaze. Now, just to show you how experienced we are, we have triple redundant microblazes in military applications, high reliability applications, and satellite applications. We have a lot of experience with putting together our own processors. Wrong clicker. And of course, we do support hypervisor. Currently, we are supporting the Zen hypervisor. We are working with third party, but it does mean you can run multiple operating systems on the application A53 processors. A little bit more about the Ultra 96 development platform. You heard a fair amount of it this morning, so I'll quickly go through key elements. It is Linaro 96Board's consumer edition, so it's a small, very small form factor, credit card size. Do want to give a blatant plug for Avnet because they are our distributor for the Ultra 96. They are rolling these out. Jim, the latest date for delivery, put you on the spot. Sometime in April. Read that as by the end of April. And so it will be available through them. They're going to be providing different bundles for availability. It has our ZU3 device. Well, what that really means is it's got the same processing system as the majority of our devices. It just means it's one of our physically smaller devices in terms of the device. Unfortunately, we always show pictures of the top of the board. And so our Zinc device is hiding right here where all the pads are on the bottom side of the board. And unfortunately, you can't even see it because we have this little wonderful fan-mounted heatsink to blow air on it to provide cooling. And you can see the entire collection of peripherals there. We do support the standard high-speed connector and the standard low-speed connector, and a listing of ports. I'm going to pause here. Any questions about the Ultra 96 characteristics? I'll talk a little bit about software availability on the next slide. Okay, if you speak up, I can repeat. Oh, the question is, do we have Ethernet on the board? The board has a wireless interface. We do not have a direct Ethernet connection. My understanding, that's not actually a requirement in the 96 board's format. One can do a USB Ethernet dongle.
I'll add, there should still be an Ethernet port on the high-speed header for lines that you can break out with mezzanine.
Thank you for that clarification.
USB to Ethernet port on there.
Will the heatsink come in the kit?
question says, the heatsink, is it included? Yes, it's included. Mezzanine cards, we'll work with the standard mezzanine cards. We'd like to invite you to our demo table on Friday at, I guess, is it noon to 2? And we're going to have a series of these boards set up for you to play with the mezzanine card. We'll have the Grove mezzanine card on there. We have pre-configured software so you can actually create code, edit the code, see things flash, buzz, etc. And so this is also available as part of one of the bundles that we're looking at. Again, just quick way for you to get started. And then we're going to provide a card image. This is to give you a really quick out-of-box opportunity to play with the board, and this is what you'll be able to play with on Friday. So that includes the Linux kernel, version 4.9, supports the Ultra 96, which means all those hardened peripherals that I showed you on an earlier slide, the Mali graphics support. It boots up to the Enlightenment desktop. It actually serves up a web page similar to what I'm showing up here. And you can hook up a keyboard and a display just as I currently have, and we'll be demonstrating. Or wirelessly, you can actually just connect to it wirelessly and on tablet access these web pages. And you can go and run any of the sample applications we have on there. You can then go in and click on any of the applications, open up the code, edit the code via an HTML editor, click a single button, and it will automatically recompile the code and begin execution of the code. Moving on, software acceleration. Question, yes?
I hope the Mali libraries are provided.
The question is Mali drivers. I'm going to have to defer that one. I do believe we have some of the same challenges you heard earlier in the earlier session. So, how do you go about taking your code and turning it into hardware? So you heard a little bit earlier from Tomas. I'll go and kind of describe the flow in a similar manner. First and most important thing is you have to sit there and profile your code. Find your critical code segments. I can tell you that if you have a general purpose application, and my worst case example is a text editor, you're not going to be able to accelerate a text editor. There's no critical code segments as far as I know of in a text editor. But if you are doing an embedded application, usually what's happening is you're bringing in a whole bunch of data, you're going crunch on that data, and then making some decisions on the end result of that data. And that means that your code usually ends up being critical in a couple functions. And so you identify those time-consuming functions. You then use our SDSOC tool, and you say, here's a function. I want you to go and take that function and convert it to hardware. And on your PC, it will then go and convert it over to hardware and then start giving you estimates. It'll actually tell you, this is how long we think it will take to actually execute that code. And you can go, okay, out of the box, I was lucky, and it's running n times faster, and that's fast enough for me. Now, kind of truth in advertising. I wish it were truly that easy to say, yes, we will always accelerate your code 100 times. But the answer is it's code dependent. Frequently, you will look at the code and you go, you know what? I want to be able to accelerate it by parallelizing it in some form. So what does parallelizing mean? Well, parallelizing means things like, okay, I'm looping through this thing 4 times, and I'm doing calculations on 4 independent array elements. In software, I do it sequentially. What if I could do all 4 of them in parallel? And so you can then tell the tool, unroll this for loop, and it will instantiate 4 parallel paths doing the hardware calculation simultaneously. So suddenly you get 4 times faster. We also allow you to do pipelining. What pipelining means is if you have a lot of code and you just do an operation here and then you do another operation on the same data and then another operation, another operation. Software, you're used to doing that in serial manner. But in hardware, we can go and say, go crunch on the first piece of data, move it down, let the second engine go crunch on the first piece of data. Meanwhile, the first engine is going crunch on the second piece of data. And you just pipeline it. And you can instantiate a number of pipeline stages. As you do that, again, you're accelerating your code. Once you have gone through that exercise, you can then say, okay, make it into actual hardware, put it into the board, and what it will do is it'll instantiate the hardware, as you heard earlier, attach DMA engines, and basically allow the data to move automatically from DDR memory to the accelerator and back to DDR memory. And for you as a software user, most important thing is it takes that function call, it keeps it the same, but it removes all the software you had and instantiates the hardware calls and the pointers to the DDR memory and the accelerators. So it becomes transparent to you that you've actually replaced the software with hardware. You download it and you run it. So, what are typical types of acceleration? And generally, my experience is that in the real world, for most applications, you'll get roughly a 10 times acceleration. And that can be huge. My favorite example is that back projection algorithm. Okay, there we got an 8 times acceleration. And you go, okay, well, 8 times acceleration, that's not too shabby. And oh, by the way, we tend to compare it against the processor we have. So we have a 1/2 gigahertz processor. So that 1/2 gigahertz processor is appearing as if it's 8 times 15. What's a 60 gigahertz processor? Okay, obviously you can't buy that. You could buy a multi-core that might start approaching that performance. How many watts will that multi-core processor run? Okay, over 100 watts probably. Meanwhile, there we're consuming just a couple watts. 16K fast Fourier transform used in signal processing, 10 times acceleration. Optical flow, typically used in recognition applications looking for movement. So here's optical flow, that's yours truly, and all I was doing was taking a picture of myself, and oh, by the way, I moved ever so slightly when I took the picture, so you can see my outline. I'm sorry. And there we got 25 times acceleration, stereo local block matching. In other words, we're actually looking for objects and their depth with the stereo camera. 25 times acceleration, 2D video optical filter, 30 times acceleration. And then this whole neural network thing you heard about this morning, 8,600 times faster. Okay, so why that huge jump of 8,600 times? And a couple pieces of magic. The first of which is neural networks happen to be very well organized, repetitive processing functions, and they tend to be large. And so you're able to have a massive amount of computations, and oh, by the way, they occur. If you look at a neural network, you'll see these diagrams that show you 2D arrays, and then they're just kind of stacked. So you're talking about processing that is done both in vertical and horizontal, because frequently we're doing image processing simultaneously, and then we're going to be doing multiple of these one after another of these planes of processing. So it's a massive amount of computation, all done locally. It means that you can move this data very efficiently and effectively within the programmable logic. And then a little bit of truth of advertising. Binary neural network. Please do attend my presentation tomorrow. I'll talk a little bit more about it. But it means that we're doing the processing single bit type operations. Happen to be extremely efficient with our lookup tables. And a little more truth in advertising. If you look at embedded processors, they're good at processing 8 bits, 16 bits, 32-bit operations. You ask it to do binary, you can do binary operations, but you're always having to add mask instructions afterwards, after you've done binary operation, so they're not real efficient at doing binary operations. So, yes, question.
Do you have any networking workload accelerators?
The question is, do we have any networking workload accelerators? We have a whole division and teams supported for data center operations, and we do have customers that do network acceleration and accelerators using our devices. Some of the, a lot of those types of accelerators are typically done by third-party partners or by the individual companies. Tomas covered the neural network example earlier. I just wanted to kind of add a few things. So first, a couple pieces of trivia. Your engine is only as good as your training. And so if you have a large data set, life is really good. In addition, we actually started out with this German roadside database. It happens to be kind of one of the standards in the industry, especially if you're looking at automotive applications. There are actually about 1,000 images in that database. We actually then went and rotated them plus or minus 7 degrees. And then we actually sized them up and down. I think it was plus or minus also 7%. The reason being is that neural networks tend to be fairly picky about, hey, I see this image, and if it's not exactly that same way, then I'm going to increase the I'm going to reduce the probability that I've got a match. So if you add a little bit of error, and in this case, just by rotation and sizing, it means you increase the recognition rate. Another fun one was there are 43 road signs. So originally all the training was done on the road signs. And neural networks work just like the human mind. And so it did a great job as long as there was a scene with a road sign in it. If there was a scene with no road sign, do you know how when we look out in the world and we look at some random pattern, and inevitably our mind will find a face, 2 eyes, a nose, and a mouth? Okay, that's because we've kind of been trained to recognize faces. Well, neural network, if all it knows is signs, it's going to find a sign in a scene where there's no sign. And so we quickly discovered that it was constantly finding signs where there were none. And so what we did was we went out and just took all these scenes and took the backgrounds, and we reran the training set with all these different backgrounds. Didn't completely eliminate the false recognition, but dramatically reduced it. So just kind of a piece of trivia. Performance results. You're going to see 2 sets of numbers. And so you see the number up here and the whole 19,000 times acceleration, in this example 19,000 times acceleration. And then on the Ultra 96 you'll see slightly lower. Okay. Well, we have different sized devices, and the original implementation was done on one of our larger devices. And on one of our larger devices we were able to clock it a little bit faster than we were able to do on the Ultra 96. Has to do with the fact on the Ultra 96, being a smaller device, we completely filled it up with the neural network. Software, also like to point out, in software, when we ran it on the A53, we could do what we call tiles, 2.17 tiles per second, versus the hardware accelerated. And then finally, in terms of techniques, there are different types of neural network engines. There's a class of engines, and so for example, you saw on the keynote the ability to recognize human beings anywhere in a scene. And that particular engine is able to do a single capture. You only look once, YOLO, of a scene and do a recognition. Other engines, such as this particular CNN, is designed to, you give it an image and it'll come and say, yes, there's a sign there and this is what I think it is. And oh, by the way, that image you give it has to be 32 by 32. So you have to go through this process of tiling. So we start out with a large image and we create two tiles, one on the left-hand side, one on the right-hand side, and we say, is there a sign there? And then we go and keep cutting smaller and smaller tiles into the scene. And that's why when you look at the recognition, you will actually see, in this example, all the blocks are the same, but when it was running, you'd actually see different sized green blocks because those were actual tiles. And this is one of the difficult things to compare. Some folks are, when they provide their number of images per second, they are using this number, which is the one we tend to cite because everyone else does, and says, hey, I'm processing 19,000 images per second. In reality, though, frequently you have to go and tile across a scene, and in this example, when we do that with 320 tiles, we're running at 94 frames per second, or equivalent. And actually, if you can switch over to the actual example. If you could switch over the HDMI monitor, please. Could you switch over to the HDMI monitor? Thank you. There we go. All right, so you saw it earlier. Things, just kind of interesting to point out is you will see different size tiles. Also, another thing you have to watch out for is a lot of times people will cite numbers. They'll go and say, I trained on 1,000 images, and then when I go back to my neural network engine, I'm getting 97% accuracy. And you go, okay, cool, what's the data set you used? Oh, I used 1,000 images that I trained on. Okay? So that's not exactly fair. What we actually did was we trained on the German side roadside database, and then we had somebody go out and take hundreds of pictures. And that's what you're seeing in these scenes. And then let's see, let me just kind of pause this. Take a look at some of the interesting parts. And so it looks like here we had a lot of success, but again, what you'll see is, okay, I recognize a particular sign, it's passed by on the right, 90% probability that it's correct. Oh, by the way, could have been a roundabout sign. Okay, here we basically came back and said everything else is less than 1%. Occasionally, we'll get some interesting results. Let me just single step through if we can get a couple of the fun ones. Okay, and here you can see, okay, here's one that came pretty challenging. 60 kilometers per hour, we got it correct, but only 17% probability. For whatever the reason, give way was 18%, bicycle crossing ahead, 3%. So a lot of this also has to do with training. Fair probability that 60 kilometer sign, maybe there were fewer samples in the database to be trained on. All right, wrapping up. We got a late start, so if someone has next session, I apologize. So a couple things, and again, blatant pitch for Xilinx. We've been at it for a while. We provide all the layers in the stack to help you get started. We start with silicon. We have these development kits. The Linaro Ultra 96 board is just one example of development kits. We have software development tools. We have hardware development tools. We have the operating systems that go on top of it. We have reference designs. Incidentally, the demo that I've just showed you is going to be one of the first reference designs that we're publishing. And then you can take all that, pick it apart, and then create your own designs. Again, please do come by our table on Friday. We'd love to have you submit a design example. Craig, go ahead and stand up. Craig is running the contest here. You can also corner him and start talking about your design examples and maybe brainstorming, or feel free to brainstorm with me. And, we can kind of tell you what we have and kind of help you give some constraints so you might be a little more successful in your proposal. But create a proposal. We're going to give you out, 30 of these boards. And it's interesting, I'm sorry, we've got 25 of these boards giving out. And I apologize, Craig. I've got an old slide in my deck for some reason. And anyways, we've got gift cards we'll be giving, and we'd like to see if we can make this a fun thing. And oh, by the way, the guy that's #1, where you're going to get press from Xilinx, will publish you, and we're going to invite you to our developers forum. We have these coming up next year. They'll be in 3 different worldwide locations. So, bottom line, if you're a software developer, I'd like to kind of just reassure you that you will be able to develop your software in kind of a development environment you're used to, that you can do this on-chip, debugging. We've got extensive libraries and IP. We've got the tools for creating that software, moving it over to hardware. You heard about SDSOC and the free license that we'll give you for 1 year. And we have pre-built reference designs that will be available with the board. Okay, a couple quick minutes for questions. Yes?
For machine learning applications, how would FPGA compare to the neural processing units? These are probably how people use them. Do you think Steiner would
Okay, so the question was, today, how does the FPGA compare to neural processing units? It's, to be honest, in my mind right now, we are in kind of the wild, wild west when it comes to neural processing engines. There's a whole bunch of these technologies that are coming in, people with good ideas on how to go and implement these neural processing engines. And you have your general purpose processors. There's no doubt in my mind that a FPGA device can create far more cost-effective, power-effective acceleration compared to a general purpose processor. Inevitably, I get the question about GPUs, GPGPUs. How do we compare? And then I invite you to go out and take a look at some of the industry literature. Tomas had one of his slides, and the answer is that there are different scenarios where we come ahead. There are some scenarios where GPUs can come ahead. But what we really believe is that we offer far greater flexibility. And when you look at neural networks, you ask people, okay, what's the network topology I should be using for my application? Their response is going to be, it depends. And it's a black art. And you need to experiment a lot. And this is where programmable logic really helps you come ahead, because you can create any architecture you want in that implementation. Okay, I think we've taken our time, run a little bit past. We got a late start. Thank you very much.